Hi everyone, what I want to do is talk you through your first lab here, okay? So, we're going to talk about precipitating calcium phosphate. You've actually done this lab, okay? You're unfortunately we couldn't finish it because you know, our stuff's still in the fume hood drying, right? So what I've got, I'll show you a sample data set. We work through that together. I'll give you a different one, of course. I'll look at the bottom of this discussion thread or somewhere, or maybe in the announcements or somewhere for sample data 2. So you'll have sample data 2 which you'll use, and you'll fill it out in the same kind of way but have different numbers, okay? So that'll be your kind of pretend lab data, okay? So let's just recap what we did. So in part A, we took a fixed amount of calcium chloride and we dissolved it in water, right? Now that's that same amount dissolved, all right? So if we look at data table 1, data table part, sample data 1. So you weigh an empty beaker, you weigh the beaker and the calcium chloride. This is pretending the numbers you got. Now your numbers for your sample data set will be different. Okay, I'll work out mine just to try and show you how to do it. So obviously the mass of the beaker and calcium chloride minus the beaker alone. So that's 47.075. And feel free to work along with yours. 46.570. 0.505. All right. Okay, now your number will be different, but remember that's right about where it should be. We kind of tried to weigh out as close to 0.5 of a gram of calcium chloride in part A as we could. If you did B, we have that on a different piece of paper in a moment. Okay, then we did our experiment. Okay, if you remember, we then add sodium phosphate. And we added an excess. If you got to that point in the notes where you know what an excess is, that's great. If not, don't worry about it too much at this time. We don't really need that information right now, okay? But then we have our reactants, okay? So we have calcium chloride aqueous plus sodium phosphate aqueous turns into calcium phosphate solid plus NaCl aqueous. Okay, and that was the reaction you had, right? Okay, now we have to balance that up. We did this as an example in the notes, and I'd really recommend try and get through that chemical composition note packet at least up to the point where it says try your lab now. Okay, so we go through a few examples and it says try your lab. Okay, so that'd be a great place to look. Okay, so try and work through up until this point. Okay, then this will make a lot more sense. Okay, so that's our equation, not balanced yet. 1 calcium, 3 calciums, 6 chlorines, 6 chlorines, 6 sodiums, 6 sodiums. There we go. So that's our balanced chemical equation. Fair enough. Okay, that's what happened. Now obviously we got this thing on our filter paper. After we filtered this, we got it on our filter paper, we dried it, and hopefully some of you had that sitting on the watch glass. That's great, right? And then we weighed it, okay? And if we go back to our data table, okay, so here's data table number 1 again, right? Okay, so again, use yours, right? Your numbers will be different. So you have the mass of the filter paper plus the mass of the filter paper and the precipitate. Just do the math there to figure out by difference. 1.549 minus 1.010 for me, again your numbers will be different, 0.539 grams. So the mass of that stuff, 0.539 grams in my example. Okay, fair enough. Now, if you're up to speed with the packet, you know that we have to figure out the theoretical yield, okay? And that's what we're doing in this lab too, okay? So the next two things are exactly like we did in the packet. So there's many examples of this in the packet, okay? in this kind of publisher's version, they've left you a tiny little piece of space here to do the work. But remember, I like to do a slides and ladders. If you can squeeze it in there, great. If you want to do a chain there, great. But I'm going to recommend you do it on a separate piece of paper. Just take a picture, send it to me, right? Okay. And then we'll work out the yield, right? Okay. So remember how this works, slides and ladders. We always set it up in the same way. Okay. We don't have to fill in the whole grid this time. In the packets, we did it, the whole thing just for practice, right? But if we plan our journey, we can make it a bit simpler. So if you think about this, right, you don't need a map of Illinois to drive to Bolingbrook, right? You just need a map of Will County, right? So if we figure out our destination and our starting point, that's what we're going to do. So we need this. We need the theoretical yield of calcium phosphate. And we're starting here with our given amount. Now, I must specify, that's kind of a little bit misleading, okay? So the mass of calcium chloride, yes, we put it here. But that number there is if it goes 100% perfectly, right? So the question is it really that amount? We'll actually work out that amount in theory and see how close it gets to this number we got from the experiment, okay? So remember, that's the number we got from the experiment. That's the actual yield. We're going to work out the theoretical right here. Okay, remember, that's not going to be the same unless we were perfect. Chances of being perfect, 0. All right, this is excess. If you look at the packet, you read on a little bit in the packet, you'll know that that doesn't affect the calculation. So molecular weights and things. Okay, now this one, calcium chloride. Give me a second to find my notes here. All right, so calcium chloride, interesting. Remember, when we work out molecular weight, it's just for one formula. Okay, so 1 calcium, 2 chlorines. That actually weighs 110.98. And our journey is down, across, and then up. Okay. The other thing we can fill in is this one now. This one, 3 calciums and then 2 phosphates, which contains 2 phosphorus, 8 oxygen. If you add that up, it's quite a lot, right? It actually adds up to 310.18 grams per mole. Okay, now we run our numbers. Okay, so grab a calculator. So I can locate mine. There it is. Okay, so nice and easy. So divide to go down. 0.505 divided by 110.98 equals 4.55 times 10 to the minus 3 moles. Now, again, your numbers will be different because, again, you're using data set 2, not data set 1. This number will be different, this will be the same, this, of course, will be different. Okay, now here's the thing. Once we've climbed down, remember, 3 moles react with 1 mole, 30 would react with 10. It's a ratio. We don't have a nice round number, we have this number. But what we do know is this one is 1/3 as less. So we divide by 3, well, I should say 1/3 as much, right? Divide by 3 to slide across. 1.52 times 10 to the minus 3. Fantastic. So from here to here, divide by 3 because 3 makes 1. All right, and then, hey, to climb back up, divide to go down, multiply to go back up, times 310.18, we get 0.47. Oh, grams. Now look, it's not the same, is it? It's not the same, but that's okay. We didn't expect it to be the same, okay? And in the next step, we'll compare it. So we go back. All right, so here, the theoretical yield was 0.470 grams. Now, again, you can write whatever you did, right? If you can squeeze it in there, great. If you want to kind of write this on a separate piece of paper on the back or whatever, take a picture, just tell me. Okay, you've got to show me the work, but there you go. So that's your theoretical yield, right? Now, remember, we actually got, and I can probably stick here, we actually got 0.539 grams from our experiment, right? When we should have got 0.470. Oh, wait a minute, it's too much. How can it be too much? Remember the note packet, it's wet, right? So there's a little bit of extra water in there. So it's okay to get numbers over 100. So the percent yield is the actual, what you got out of the oven, over the theoretical, what you should have got, times 100 for a percent, which equals actual 0.539 grams over theoretical 0.470 grams times 100 for a percent. It's going to be over 100, but what is it? 0.539 divided by 0.470, 115%. That's okay. It's allowed to be bigger than 100 because of experimental error. Okay, so you know, anything between 80 and 140, believe it or not, in this experiment is okay. All right, so that's how you'd complete part 1. Okay, so complete your similar page, but it will have, you know, data set 2 up there. All right, now back to it. So when we did unknown, you know, we'll just call it unknown sample data 1, right? So, you know, you got, you know, the same kind of thing here, but this was for B. It was exactly the same procedure, okay? But we just do the math differently, okay? So this is going to be different, and this is going to be different down here. And I'll show you how to do that on a piece of paper in a second, but this top part, basically the same, right? So let's just work out those numbers again. You know, follow along with your data table. Your numbers will be different, but the same idea. So the mass of beaker and unknown mixture, mass of beaker, subtract mass of unknown mixture, 46.005 minus 45.250 equals 0.755 grams. Makes sense, right? Because I asked you to use a little bit more because the unknown mixture contains a less amount of calcium chloride, so we need more of it for the same effect, essentially. Okay, so you know, work out your number there for B, all right, for sample data 2, and then, you know, we go through same as before. We take it out of the oven, we'd weigh it. 1.412 minus 1.025 equals 0.387 grams. Fair enough. All right, now this is going to be a different procedure, okay? We have to work backwards because the goal, now remember, let me draw a picture actually, all right? Let me just put this to one side. Let's not lose track of what we're doing here, okay? So, B. Unknown. For the unknown, we had this little container. It was some percent of calcium chloride and some percent of other. And we don't care what the other is. We just want to know what percent by weight it was. Was it 50% by weight? 10% calcium chloride? What was it? Okay, now to work that out, if you think about it, we have to work backwards to the grams of calcium chloride in our grid. Okay, so we're going to do the reverse math. Okay, so we're going to set up the same exact table we had before. I'll show you that quick. We're going to set up the same grid, but we're going to go in a reverse direction. Okay, we're going to assume the number we get in B is the perfect answer, which is a faulty assumption, but you know, we have to do it for the math, right? So we're going to run it backwards and work out the grams of calcium chloride in the unknown. Okay, so let's do that. So we've got the same grid setup, right? Calcium chloride plus, and I'm going to write it balanced already because it's the same equation. Here we go. Okay, so everything in terms of the balancing and the molecular weights carries over. It's the same equation, okay? But here, this is our destination, okay? We need to figure out how much calcium chloride is in, let me just move that up, how much calcium chloride is in that unknown mixture, okay? Starting here and moving in this direction like that, okay? Now, if you remember, again, your numbers will be different, right? Okay, your numbers will be different. We're going to assume that's perfect. it worked out perfectly, right? So that's the exact number we want, 0.387. Okay, fair enough. And then we'll fill in the rest. Okay, fill in the rest. The molecular weights are the same as before. Fair enough. Okay. And then we just work it through. Okay, so this is our direction. Divide to go down. Again, your numbers are different. So just work it through with your numbers. Divide it out. 1.25 times 10 to the minus 3. Now here, because we're going in the reverse direction, 1 came from 3, so that's 3 times bigger. I'm going to multiply by 3. Slide across, multiply by 3, 3.74 times 10 to the minus 3. Divide to go down, multiply to go up, times 110.98 equals 0.415 grams. Okay, so just I recommend pausing there, okay, using this as a template to work your data from data set 2 backwards, okay, until you get to this number. And remember, that is calculated to be the mass of calcium chloride in this mixture. All right, so go here. You know, you can, if you can squeeze it in there, great. If you did it on a different piece of paper, fantastic. Okay, but our number was, let's remind ourselves, 0.415. That's for this data set, right? Okay. Now, this is where it's different down here. What percent is in our unknown? Okay. Now, to do this, we have to remember how percent mass works. Okay, so it's the part, if you remember we did this before, over the whole times 100, which will equal the mass of calcium chloride, that's our 0.415 number up here, right, over the mass of the mixture, that's the whole, times 100 for a percent. Okay, so what do we get? Well, the mass of calcium chloride, let's move that just a shade, 0.415 divided by the mass of the mixture. Now we've got to look back at the data sheet for that, right? The mass of the mixture is here, 0.755. So 0.415 grams out of 0.755 grams, okay, times 100 for a percent equals, let's do this math real quick, 0.415 divided by 7, 0.415 divided by 0.755 equals 50, wow, if you round up, 55%. Okay, that's the actual number I got on my calculator. 54.96, rounded up 366. Okay, so that's the answer. Okay, 55.0%. See that? Typo. It says percent, right? There we go. All right. Okay, so there we go. So we have a type A. Let's just recap, all right? This will be useful for the questions, all right? So we have a type A, where you go from left to right, work out a theoretical yield. That's the traditional question. Then we have something a little different. We have the type B question, where we assume the experiment went perfect. From the mass of our product, we work backwards to find out how much calcium chloride it came from, and hey, how much of that as a fraction, as a mass fraction, was in our mixture. Okay, all right, now, so work on that. Okay, work out for sample number 2, part A and part B. All right, now, when it comes to the questions, all right, when we look in our packet, okay, and the most important part of this, and as I kind of mentioned when we did this pre-lab, I said, hey, we'll come back to class and we'll work on this together in class. Well, yeah, here we are, right? So, bottom line is this, you're going to fill this in, okay? You're going to work on these questions, and this is going to be, frankly, you know, a big fraction of the grade for this lab, okay? So the trick is looking at these questions and figuring out, hey, is it a type A problem, which is just the straight up theoretical yield left to right? Or is it the reverse problem, working backwards to find how much is in a mixture, okay? Now, when we look here, we have a 0.5 gram sample of stannous fluoride, sorry. So a 0.5 grams sample of stannous fluoride, that's this guy, okay? Gave a 0.5 precipitate, that's this guy, all right? So it says calculate theoretical yield. So this one here is clearly a type A, right? So do your grid, there's plenty of room for it. Go that way, work out that number. Okay, so this is going to be 0.5 here, isn't it? Okay, work out this number and then compare it as a fraction percent to this number, okay, mass percent. 0.5 precipitate. So that's not 0.5 in there. We're going to work out what it should be, and then that's what it actually is out of the oven, okay? And then work out the percent yield. And there we go. Usually going to be pretty high, probably in the 90s, okay? So, you know, these things, when we do them, you know, in industry and places like that, they're usually pretty high percentages, all right? Okay, next one. Oh, toothpaste. Interesting. Is toothpaste a pure material? No, it isn't, okay? The thing about toothpaste is the fluoride, which is actually tin fluoride, in the toothpaste is there as literally a poison, okay? And it poisons the bacteria in your mouth, okay? Kind of a funny story. When my son was like literally 4 years old, we took him to the kid's dentist and, well, Brendan, we gotta check your teeth for the sugar bugs, you know, because that's, you know, that's the bacteria in his mouth. And he looks at the dentist and he says, sugar bugs? You mean bacteria? And the dentist said, yes, I do. Okay, now, what the fluoride does in the toothpaste, it kills the bacteria, but it doesn't kill you because it's in very small amounts, right? It's like 1-2% of toothpaste is fluoride. And that's the kind of number we're going to get here. So it's going to be one of those backward jobs, okay, from here, to find out the mass of tin fluoride in a 5 gram sample of toothpaste. So the mixture weighs 5 grams. And if we start with 0.075 here and run it backwards, what mass do we get? What is that as a percentage of 5? Okay, so it's obviously a B type. Run it backwards, and it's going to be in the region of 1-2% down here as an answer. Okay, so first one's going to be a high number, second one's going to be a real low number. All right. Third and fourth, well, here we go. Now this one, oh, we seem to have a fixation with teeth. So tooth enamel. So the hardest substance in the body is tooth enamel, which is mostly composed of this thing. Mostly, right? Okay, so you can dissolve tooth enamel with hydrochloric acid, all right? And you can do this whole kind of find out how much of this is in the tooth enamel. So tooth enamel is a mixture, okay? So it's like, you know, if we had 1 gram of tooth enamel and it gave us 0.925 grams of this, yes, it's another B backwards, right? It's a mixture. So find out how many grams of tooth enamel, sorry, how many grams of this thing are in the tooth enamel, divide by this times 100 for a percent. Now this guy's going to have a very large molecular weight. There's 10 calciums in there, 6 phosphorus, 24 oxygens, and then another 2 and another 2 hydrogens. Okay, so that's going to have a big molecular weight. Okay, so don't be surprised if that's a really big number there. Okay, so that's a B, it's a backwards B. Now the next one, the last one, optional, you know that's code, right? That's code for extra credit. All right, so milk of magnesia, magnesium hydroxide, okay? You take that when you've got an upset stomach, right? Why? Because if you've got an upset stomach, you've got too much acid in your stomach, and hydroxide will calm your stomach down. It will get rid of that extra acid. Okay, so the thing of it is though, when we make this stuff, yeah, this is going to be a limiting reactant problem. If you read and finished the packet, chemical composition, you'll know how to do this, okay? So maybe you want to kind of delay this one until you finish the packet. If you finish the packet, hey, it's a limiting reactant problem, okay? So it says magnesium hydroxide is prepared from magnesium sulfate and sodium hydroxide. A solution containing 100 grams of this one, 70 grams of this one, okay? You're going to climb down and then decide which one runs out first, right? And it's in a 2-to-1 ratio, so be careful, right? I need twice as much of this than I do with this. Whichever you determine to be limiting, slide across, climb back up, and you get that number, okay? So calculate the mass of this produced. It's a limiting reactant problem, so that's a big hint. Put it there, okay? Give you a +10 lab extra credit for that. Got it like that, right? Okay, so feel free to talk to me, talk to each other in the discussion area. But my biggest kind of recommendation is finish or get as far as you can comfortably through that chemical composition packet before trying this lab. And then this lab then basically turns into practice of that material. Okay, if you try this too early, it won't make sense, all right? So do that. I'll put the deadline up in the, I'll decide what the deadline is. I'll be reasonably generous with the deadline, but do take note when I write it up in the discussion area, okay? Again, ask each other, ask me if you've got questions. See you next time.